All right, we're about to go on an epic journey. We're going to tackle the biggest story imaginable, the entire 13.8 billion year history of our universe. We'll go from the very first moment to, well, everything we see around us today.
The whole story really starts with this idea. It's so simple, but it's also incredibly profound. This is the ultimate origin story, right? But it immediately makes you ask, yeah, how could we possibly know? I mean, no one was there to see it. This is where science gets really cool. It becomes this amazing cosmic detective story where we use clues left behind in the universe today to piece together what happened all those billions of years ago. Okay, so first things first. Let's talk about the method. How do scientists take what we see today and turn that into a detailed history of the entire cosmos? Well, the biggest clue we have is a pretty simple observation. Pretty much all the galaxies out there are moving away from each other. The universe is expanding. So if you just run that clock backwards, what does that mean? It means everything in the universe must have been squeezed together into this unimaginably hot, dense little point. And here's the really wild part. We can actually test our ideas about what that early, hot, dense state was like. We have these giant particle colliders that smash particles together at insane speeds. And for a split second, they recreate the same high-energy conditions of the universe in its first moments. It's kind of like having a time machine that can only visit the very, very beginning. So now that we know how we know, let's wind that clock all the way back. Let's go to that first absolutely critical second, a moment more bizarre and more transformative than any other in history. To really get what happened in that first second, we first need to talk about a concept from physics called a phase change. And trust me, it's something you already see every single day, but it also happens to govern the entire cosmos. Just think about what happens to water. You start with a snowball, right? It's solid. Its molecules are all locked up. You add a little energy, some heat, and boom, it becomes liquid water. Add even more heat, and it turns into steam, a gas. Its fundamental nature changes. Well, the early universe did the exact same thing, just in reverse. As it expanded and cooled, it went through these dramatic phase changes. So, in the very earliest, hottest moment imaginable, the four forces that run our universe today, that's gravity, electromagnetism, and the two nuclear forces, they weren't separated at all. They were actually merged together into this single, unified superforce. And as the universe cooled, this superforce split apart in this cascade of phase changes, creating the laws of physics that we live by today. Okay, let's jump forward just a few minutes into the universe's life. It's now cooled down just enough to stop being this soup of pure energy and to start building the first tangible stuff. The whole cosmos became a nuclear forge. Look at these first key milestones. For this super brief window of time, only about 17 minutes, between 3 and 20 minutes after the Big Bang, the entire universe was acting like the core of a giant star, fusing the very first elements into existence. And then it just stopped. The universe had cooled down just enough that fusion wasn't possible anymore on a cosmic scale. And what was the result of that 17-minute-long cosmic cooking session? Well, it was this exact ratio of elements. About 75% hydrogen, 25% helium, and just a trace of other stuff. This primordial mix is exactly what we still see in the oldest stars today, and it's one of the absolute strongest pieces of evidence we have for the Big Bang. So for the next 380,000 years, the universe was just this hot, glowing fog. Light couldn't travel anywhere. But then, a truly pivotal moment arrived, when the entire cosmos suddenly, and I mean suddenly, became transparent. This event is called recombination. See, before this moment, the universe was just this chaotic soup of charged particles. Photons, particles of light, couldn't get anywhere without immediately bumping into a free electron. It was like trying to walk through an incredibly dense crowd. But as the universe cooled, electrons finally got captured by nuclei, forming stable, neutral atoms. All of a sudden, the crowd was gone, and the photons were free to travel. The entire universe flashed, releasing this incredible wave of light that has been traveling across space unimpeded ever since. And we can still see it. Today, it's stretched out by cosmic expansion into this faint microwave glow coming from every direction in the sky. This is literally the baby picture of our universe. It's the oldest light we will ever be able to see. But here's where it gets really interesting. This ancient light held a clue. It wasn't perfectly uniform. And those tiny little imperfections pointed to an even more dramatic, even more violent event that happened way, way earlier.
The temperature of that first light is incredibly smooth across the sky. But there are these minuscule fluctuations, tiny hot and cold spots that differ by only 1 part in 100,000. Now, that may not sound like much, but our theories predicted the universe should have been way lumpier. This incredible smoothness was a huge puzzle.
To explain this, physicists came up with a truly mind-bending idea. They called it inflation. The theory goes that in the very first fraction of a second, a phase change dumped a ridiculous amount of energy into the fabric of space-time itself, causing it to expand faster than the speed of light. It smoothed everything out, kind of like pulling a wrinkled bedsheet taut.
But inflation did something else miraculous. It didn't just smooth things out. It also took these tiny, microscopic quantum jitters and stretched them to cosmic scales. These slightly denser regions became the seeds for everything that would come later. They were the spots where gravity would have just a little extra pull, gathering matter together over millions of years to form every star and every galaxy we see today.
And, well, that brings us to today. This incredible story explains our cosmic origins, all the way from a quantum fluctuation to the Milky Way. But it also leaves us on the doorstep of some of the biggest and most profound mysteries in all of science.
I mean, even with this amazing story, these are the questions that keep physicists up at night. What is all this dark energy that's pushing everything apart? What about the dark matter holding galaxies together? And of course, the biggest questions of all, where did this universe even come from? And what, if anything, came before the Big Bang? So we'll leave you with this final thought to chew on. If time and space themselves literally began with the Big Bang, then asking what came before it, well, it might be like asking what's north of the North Pole. The question itself might not even make sense. Figuring that out is the next great chapter in our cosmic detective story.